So last time we were talking about the electrophilic aromatic substitution reaction. I want to go over some of that just again. So we talked about the general EAS mechanism, where a generic electrophile will react with an aromatic ring like benzene, and we get a substitution of a hydrogen for an electrophile, right? And so walk me through that mechanism real quick. What's the first step? That's right. So we have the pi bond attacking the electrophile. We end up with a carbocation intermediate, which is resonance stabilized, right? And then loss of the proton ultimately gives us our ring back, and of course the proton usually gets helped to be displaced by the counter ion that's around that I'm not showing on this particular mechanism, because that can be different in a variety of them. So what's the trick? The trick isn't the general electrophilic aromatic substitution reaction. It's the easiest reaction I've ever shown you. The trick is, how do you get the electrophile, right? And what electrophiles did we talk about that we can do EAS with? We talked about the halogens, right? So like Cl+, I'm going to put that in quotes, and Br+, right? What else? What other things can we use for electrophilic aromatic substitution? What do you think, Matt? Oh, we could. That's a Friedel-Crafts reaction, so carbocations can do this. Okay, what else? What other electrophilic aromatic reactions did we talk about? One slide on that PowerPoint last time. Nitration, so NO2+, and what else? Sulfonation, SO3H+, right? So the question is, how do we generate E+ in these reactions? And that's what I want to finish up today and then move into the next set of slides on our PowerPoints. So if we're thinking about halogenation, and let's say Karina wants to do chlorination of a benzene ring. She needs Cl+. How likely is it, do you think, that we'll have Cl+ that we can just go buy in a bottle and throw in the reaction and be done? Not at all, right? Cl+ doesn't make a whole lot of sense because chlorine's very electronegative, right? But it turns out that if you take chlorine, which is a diatomic molecule, drawing all the electrons here, and you add iron trichloride, you get the equivalent of Cl+. Does anybody know what type of reagent iron trichloride is? Is it a Lewis acid or a Lewis base? It is not a trick question. It is. It's a Lewis acid. And so chlorine, having these lone pairs of electrons, can function as a Lewis base. And we can get a Lewis acid Lewis base adduct forming. And now we have an electrophilic source of chlorine. Which chlorine atom on that complex behaves as Cl+? Which one? Why? It bears a formal positive charge, but it is not the one that gets attacked by the nucleophile. It's the one on the end. That's right. This one's actually pretty shielded from all this stuff, right? But what can happen now is our aromatic ring will react and that's how you get that intermediate. Now, FeCl3 is a catalyst, meaning that it has to be regenerated. So FeCl4 minus actually will dissociate in solution to FeCl3 plus Cl minus. And it's the chloride that comes in and removes the hydrogen from the resonance stabilized carbocation intermediate. And you get HCl plus the substituted benzene in the final product. So you get FeCl3 regenerated plus HCl plus the product. Okay? Now it turns out that for practical reasons, a lot of times people don't add iron trichloride. They simply add iron to the solution. They'll take some iron shavings and add in there. Can anybody tell me why that will also work? The chlorine's already there. So what happens when the iron comes into contact with chlorine gas? It forms iron trichloride. That happens spontaneously. So a lot of times chemists will actually literally go get a nail, grind it up, throw it into the reaction mixture, make a little iron trichloride in situ, as we call it, and let the reaction proceed. So these reactions can be with iron trichloride or iron in the presence of chlorine, and you get the same thing. If we're doing bromination, what would the catalyst be? Iron tribromide, but the same kind of process occurs, okay? So let's think about nitration. Okay? Now, what do I need to generate the electrophile? What reagents did I say we used? Sulfuric acid and what else? That's right. So if we take benzene and a mixture of HNO3 and H2SO4, we will do the nitration of benzene and get nitrobenzene. Now, how we generate NO2 from this? We need to look at the Lewis structure of nitric acid. And here's what's really strange to a lot of people. Nitric acid is going to function like a base in the first step. It can get protonated by sulfuric acid. Can anybody tell me why that can happen? That's right. So nitric acid being weaker means that it can function as a base. And so sulfuric acid, of course, is a strong proton donor. We protonate the nitric acid. Water is going to readily leave. And you end up generating NO2 plus. That then reacts in the general electrophilic aromatic substitution reaction. And we're done, right? Sulfonation occurs by taking what reagents? What do I need? That's right. So what's the Lewis structure of SO3? What's it look like? Think back to your Gen Chem. Central atom with three other things. What does it have to be? Trigonal planar, right? So we have sulfur trioxide. And in sulfuric acid, we have a strong proton donor. And that's how you generate SO3H+, which then can go on and do electrophilic aromatic substitution. You need to know by heart each and every way that these electrophiles get generated. You do not need to second guess how these things are formed, okay? You need to know if you need NO2, what reagents you need. You need to know if you need SO3H to do the electrophilic aromatic substitution. You need to know all your reagents by heart, okay? The half note card is no longer an option, right? So it's time for things to start to be committed more to memory about things that you need, okay? Now the other thing that we talked about was the electrophilic aromatic substitution reaction involving carbocations, and those two reactions were called what? Whose names did they bear? Friedel-Crafts alkylation and Friedel-Crafts acylation. In the alkylation reaction, what reagents did we use? Aluminum trichloride and what else? AlCl3 is just AlCl3. What else did we need? We need an alkyl halide, okay? And so basically what happens is when you take an alkyl halide, let's take 2-chloropropane, AlCl3, you can generate a carbocation which can then do the electrophilic aromatic substitution reaction. We're generating real carbocations here. So what do we have to pay attention to? Rearrangements. And so just because the halogen's on a particular carbon doesn't mean that's where the bond is ultimately going to be formed to the aromatic ring, because you will have rearrangements occurring. Okay, so if you start off with a secondary alkyl halide and that can rearrange to a more stable tertiary carbocation, it will. Okay, and there are examples in the PowerPoint that you need to go back and look at. Okay, that's not true for Friedel-Crafts acylation, because what's the reagent that we need there? AlCl3 and what else? An acid chloride. That's right. When this reacts with aluminum trichloride, you get AlCl4 again, but you get what's known as an acylium ion. Why do we not see rearrangements? Harrison, why do you think we don't see rearrangements here? What do I have to see rearrangements? I have no carbocation, do I? That carbon is positively charged partially. I can draw a resonance structure which puts the carbocation on the carbon, and that accounts for its reactivity. But of those two resonance structures, which one is the major contributor and which one is the minor contributor? And why? Okay, so if oxygen is more electronegative, would it want the positive charge? What does the top one have that the bottom one does not? And an octet. Every atom in the top one has an octet around all atoms. The bottom one does not. So the top one, even though oxygen's bearing a formal positive charge, actually is the major contributor because of the octet rule. All right. So today we're going to continue talking about electrophilic aromatic substitution reactions on substituted benzenes, benzene rings that already have a substituent. That's going to lead us into this concept of activators and deactivators. Not all aromatic rings react fast. Some are slower than others. We're going to have this concept of ortho, para, and meta-directing substituents. And if we have time, we'll get into the limitations of all these things. Okay? So we know that many aromatic rings, or benzene rings, will undergo electrophilic aromatic substitution. Okay? If we have a substituent that donates electrons to the aromatic ring, Do you think that's going to make the reaction go faster or slower? Think about the mechanism. What's the aromatic ring doing in that first step of that general EAS reaction? It's donating its electrons to the electrophile, right? So if I have a substituent that's putting more electrons in the ring, so to speak, what's it going to do to the rate? Longer? If I have more electrons in the ring, or more electron density in the ring, that ring is going to more readily give up those electrons or hold on to them tighter. That's right. So the reaction should go faster. If I have a substituent that pulls electrons from the ring, what's that going to do to the reaction? It's going to slow it down. That's right. So if I have a substituent on the ring that makes the reaction go faster, then we say that that is an activator. It activates the reaction, makes it go quicker. If we have a substituent on the ring that withdraws electrons from the ring, we say that that's a deactivator. It makes the reaction go slower than the unsubstituted benzene. Okay? It's all a relative argument. Okay? Now, there are several ways that we can think about electron donation and electron withdrawing. There's the inductive effect, and that just deals with electronegativity. We know that nitrogen is more electronegative than carbon, so nitrogen's pulling electrons to itself, right, within that bond. That is inductively withdrawing electrons. We know that the methyl group, okay, inductively donates electrons through hyperconjugation. You'll remember that in terms of the carbocation stability, right? So it's an inductive electron donating group to have an alkyl group, okay? So alkyl groups will activate the aromatic ring, and electron withdrawing groups will deactivate the aromatic ring. However, if we look at our aniline example, is that the only thing that I have to take into account? Is inductive and based on its electronegativity? What else does the nitrogen have on that molecule? It has a lone pair. What is that lone pair doing? Does it do nothing? Oh, that's right. So by resonance, it can donate electrons into the ring, right? We can draw resonance structures. Help me with that. Sarah, how would I do that? I draw aniline. How would I show that it is resonance pushing electrons into the ring? How would I do that? What do I need to draw? You need to push arrows. Okay, that's true. How am I going to push my arrows? Okay, can I just do that alone? Why not? I've got to draw another arrow. Why? That's right, 5 bonds to that carbon. So I need to break a bond, right? So I can draw resonance structures. And now I can see that those electrons have been delocalized into the ring. Can I draw more resonance structures than this? Yes, right? I can push. And I can draw another one, right? So I can draw multiple resonance structures where the electrons aren't just on the nitrogen atom but delocalized into the ring. That effectively makes this aromatic ring more electron rich, and so it should react faster or slower in an electrophilic aromatic substitution reaction. Faster. It should react faster than benzene, which does not have a substituent. Okay? And so you can see the resonance structures that you see here. Where on this structure, is there never a negative charge? Okay, that's true. Where else is there never a negative charge? Within the ring. Okay, the carbon connected to the nitrogen, and where else? Notice we can have a negative charge here, we can have a negative charge here, and we can have a negative charge here, but we can never have a negative charge here and here. Right? So what does that mean in terms of the reactivity? If an electrophilic group was to come in and react, where might it react? Where there's electrons or where there are no electrons in terms of charge? Where there are electrons. I'm an electrophile. I want electrons because I'm positively charged, right? I'm going to be attracted to the more negatively charged regions. So we would predict that aniline would react with an electrophile at either this number 2, number 4, or number 6 position. Would all of those be identical products? No. Yeah, we're going to get into orthometapara, that's right. Okay. Now, if we look at something like benzaldehyde, right, has the carbonyl that is directly attached to the benzene ring. And I know that oxygen's more electronegative than carbon, so I can push those pi electrons up onto oxygen and get a resonance structure where the carbon that's directly attached to the aromatic ring is positively charged. That's going to have the effect of pulling electrons out of the benzene ring. Okay? And as such, we can draw multiple resonance structures. Since we're pulling electrons out of the benzene ring, this is going to deactivate the reaction. Why is this going to deactivate the reaction, Katie? Okay. Okay. Because an electrophile wants electrons, right? And if I'm pulling electrons out of the ring, that's going to slow that reaction down, right? It's going to take longer for that reaction to occur. And in fact, if my electron withdrawing group is really strong, it'll shut the reaction down completely. We'll talk more about that later. Benzaldehyde won't shut it down completely, but it'll slow it down significantly. However, if I'm an electrophile and I was going to react with benzaldehyde, where would I want to react? What do you think, Maggie? If you were positively charged, where would you want to go on that ring? Or where would you not want to go? That's right. That's right. So you would go to the areas that don't bear the formal positive charge. So where is that? I can have a positive charge at carbon number 2. I can have a positive charge at carbon number 4 and at carbon number 6, but I never have a positive charge at 3 and 5, right? So if I was to do an electrophilic aromatic substitution reaction on benzaldehyde, I would predict that the electrophile would go to positions 3 or 5, known as meta, which we'll get to in just a minute. So groups that activate the reaction, okay, are going to increase the reaction relative to unsubstituted benzene. The rate's going to be much faster, and it's going to direct that incoming electrophile in either positions 2, 4, or 6. If I have an electron withdrawing group on my aromatic ring, something that can pull out electrons, okay, usually by resonance, that's going to direct the incoming electrophile to positions 3 and 5. Okay? So it's very, very important in these reactions that you be able to identify what type of substituent you have on the aromatic ring, whether that's an activator or a deactivator, and that'll let you know how that new group is going to come in. Okay? All right. Now, we all know that oxygen and nitrogen are electronegative, and inductively they're withdrawing electrons from the ring.
You said electron donating effect. That will give you the 2, 4, 6?
Yep.
Okay.
Okay. But oxygen and nitrogen that are bound directly to the aromatic ring Those lone pairs are in resonance with the aromatic ring, so they donate electrons to the aromatic ring. So even though nitrogen and oxygen are very electronegative, they activate the ring by resonance. Resonance usually wins out here, okay? So you end up with the aniline and the phenol group being activators. The halogens look like an analogous situation, right? It's an electron withdrawing group with lone pairs. Okay. These are the anomaly. They will direct the incoming electrophile to positions 2, 4, and 6, but the reactions actually occur slower than the unsubstituted benzene. They are the only ortho para-directors, okay, meaning 2, 4, and 6, that are also deactivators. Everything else that is an activator is going to be an ortho para-director, and everything else that is a deactivator will be a meta-director. Okay? It's the halogens that are a little odd with that respect. Okay? The alkyl groups, of course, we just mentioned this, are activated because the R group, whatever the case may be, some typical alkyl group, is going to donate electrons into the aromatic ring by hyperconjugation. The same kind of argument we made for the stabilization of carbocations by hyperconjugation. Okay? So a substituent that we already have on benzene, we can sum it up here from what we just saw. If we have a substituent on benzene, we can predict whether or not that substituted benzene will react faster or slower than unsubstituted benzene. If the group that's attached to the aromatic ring can donate electrons to the ring, it's going to be activated, and so the reaction will occur faster than unsubstituted benzene. If we take a substituent that's going to withdraw electrons, it's going to deactivate the ring, it's going to go slower, right? And that substituent is going to direct where that new group goes, because we looked at those resonance structures, right? An electrophile is going to want to go where there are more electrons or where there are no positive charges, right? This has real consequences. So for example, you can take phenol and you can dissolve it in benzene, and you can add nitric acid and sulfuric acid. What gets nitrated? The benzene or the phenol, because it's activated. And so you would end up plus the other isomers. The benzene will remain unreacted because the reaction of benzene with the NO2 plus is going to be really slow compared to this. This just reacts with all the electrophile that you generate, okay? At least as long as it exists, okay? Now, if we took nitrobenzene and benzene and we tried to nitrate it, what would happen? What would get nitrated, the nitrobenzene or the benzene? Nitrobenzene? Benzene, because nitro is an electron withdrawing group, not aniline. Okay, aniline's a little different. Okay? So let's look at some examples. Let's suppose Gabby comes into the lab and she takes toluene, a common organic solvent. It's nothing more than methylbenzene. Okay? And she decides to put a bromine on it. So she takes liquid bromine and adds some iron or iron tribromide. She runs the reaction. She goes and looks at the NMR. And what she finds is that she gets bromine at the 2 position and bromine at the 4 position. So when we have this 1-2 relationship, we say that that's ortho. And when we have this 1-4 relationship, we say that that's para. Okay? That adds up to 100%. Notice what's absent. They say a trace, but it would be so small you couldn't really detect it. It's meta. Okay? So she's going to end up with 2 isomers of this product and that she's going to have to separate. How might she separate the mixture? Do they have to have the same physical properties? Everybody shaking their head no. Tell me why.
Well, they're not the same molecule.
That's right. They're not the same molecule. They are different. Okay? So, how might she go about separating the 2? That's possible. That's possible. Well, let's assume you want to just do a physical separation without reacting one over the other. How would you do that? Melting point is just a characteristic of the compound. How would we do a melting point to get a separation of one isomer from the other? All right, maybe we could do distillation. They should have different boiling points, right? So we could distill them. Anything else? Chromatography. They should have different RF values on a TLC plate. Okay? Anything else that you can think of? Those are the big ones. One might be a crystalline solid. You might be able to recrystallize it as a possibility. Both of these are actually liquids, but nonetheless, you could think along those types of lines. Okay? If Paige came in and took nitrobenzene and wanted to put another nitro group on it, she would find, number one, that the reaction would occur quite slow because nitrobenzene is deactivated. The nitro group is an electron withdrawing group. Can anybody tell me why the nitro group is an electron withdrawing group? It does. That's definitely part of it. What's the next part? What's the formal charge on that nitrogen of the nitro group? It's positively charged. So you have a positively charged atom directly bound to an aromatic ring. So it is a strong deactivator. And in fact, Paige would probably find that this reaction to go to completion would take several days. Okay? Still possible to do, and there's other things you can do to speed the reaction up, of course. But just as written, at room temperature, it would take a long time for this to go. And what would she find? She would go to the NMR and she would find that 93% of her material is actually the meta isomer. Less than 10% would be the ortho isomer. So the nitro group must be a what director? Meta director. That's exactly right. Yeah, you get meta. Now, how would she separate these? Same way. Maybe boiling point, maybe doing some type of chromatography. Maybe one of them's a crystalline solid and the other's a liquid. Okay? In this case, they're both liquids. But those are the kinds of things you'd be thinking about. Okay? Probably boiling point is what you'd use for nitrobenzene. Okay? You need to commit these to heart. Okay? Because there are 3 types of substituents, general types. Okay? The first is the activators that are orthopara directors. Okay? Orthopara directing and activating. With the exception of the R group, simplify the list for me. What else? What's more important than nitrogen or oxygen? Lone pairs. So this means that that's the atom that's bound to the aromatic ring, right? Notice in all cases, the atom that is bound to the aromatic ring has a lone pair. And that's right, it's all nitrogen or oxygen, but it's the lone pair that's important. The alkyl group, okay, is an activator by hyperconjugation, so it's a little different, okay? So if Carl came into the lab with a sample of methylphenyl ether, so aromatic ring, oxygen, methyl group as an ether, would you predict that that's a activator or a deactivator? What do you think, Rose? Methylphenyl ether. Would that be activated or deactivated? The aromatic ring. So it would be activated. And so you would predict that the electrophile would go to what positions? Ortho and para. Okay? You'd get a mixture. You can also have a series of ortho-para that are deactivating. And that's all the halogens. So if Brienne comes into the lab with iodobenzene and she wants to do a reaction, an electrophilic aromatic substitution reaction, she would predict that that reaction would go such that the electrophile would go in position 2 or 4, ortho and para, but that the reaction would actually be slower than benzene itself. The reason is because fluorine's extremely electronegative. Okay, and so what it can donate back through resonance is actually fairly minimal compared to what it's withdrawing. So it deactivates, okay? But it is an ortho-para director because of the resonance structures that we can draw. And then all the meta-directors are shown here. Aldehydes, ketones, esters, carboxylic acids, nitriles, sulfonic acids, nitro, and ammonium are all deactivators and meta-directors. And notice as you go down that list, the arrow is saying it's increasing deactivation. Okay? So if Sarah wanted to do a electrophilic aromatic substitution reaction on nitrobenzene, she can predict probably that it's going to be so slow, she's not going to be ready by the time lunch is done, right? She's going to have to wait and monitor the reaction, maybe heat it up a little bit to get that to occur, okay? Commit these to memory. I don't say that very often, but these you need to have committed to memory. On the next exam, you will have to know the electrophilic aromatic substitution reaction, you'll have to know the directing effects, and you'll have to know whether something is activated or deactivated. And you'll probably need to know all those in a single question, okay? So, you need to know approximately. You should know that the nitro and the ammonium are certainly among the strongest activators. You need to know that aniline and phenol are among the most activated. But I'm not going to ask you, is that 10 times, 50 times, whatever the case may be, okay? You need to have a general feel. All right, let's skip that one. So if we look at why these different groups activate or deactivate the ring, there was the resonance argument that we just talked about, right? If we have something that's pulling electrons out of the ring, that should slow the reaction down. That's only part of the truth. We all know that reaction rates have to do with the barrier over the rate-determining step, right? And what we just explained by just simple resonance structures doesn't adequately explain that. Okay? It gives us some hint. Certainly tells us why they're ortho, para, or meta-directors, but it doesn't completely explain why the reactions are either enhanced or deactivated. So for example, we know in all cases, the electrophilic aromatic substitution reaction, that first step is the formation of that resonance stabilized carbocation or rhenium ion. That's unstable. Why? Even though I said resonance stabilized, why is that going to be the tallest mountain that we have to climb? There's two main reasons. What are they? Okay, so it has to do with, what's the term for that? Aromaticity, right? So we're going from an aromatic starting material to an intermediate that is aromatic, non-aromatic, or anti-aromatic. What do you think? What do you think, Katie? You look like you want to say something. It is non-aromatic. That's exactly right. It's not completely conjugated, right? Remember, anti-aromatic has all the rules of aromaticity, except Huckel's rule changes to 4n, equal the number of pi electrons, right? This is not a completely conjugated system, right? So it is non-aromatic. So we're going from an aromatic to a non-aromatic intermediate. That's going to be the largest energy barrier. But anything that can help lower that energy barrier is going to do what to my rate? Increase it. Anything that's going to increase that barrier is going to do what to my rate? Increase it, right? So anything that's going to increase the barrier will increase the rate. Anything that decreases the barrier will increase the rate. I think we got that. Think about it. If I lower the barrier, will the rate go up or down? The reaction goes faster. The reaction rate increases. If I increase the barrier, the reaction goes slower. That's right. Yeah? Isn't that what I said? Did I say increase twice? I may have. Anyway. The reason has to do with the fact that if we can stabilize this intermediate, that should lower the energy barrier. Okay? Whose postulate stated that we learned about before? Nope. Whose postulate did we talk about? Where if an intermediate, a transition state will look like the intermediate that it's closest to an energy. Hammond. That's exactly right. So, if you look at that, the transition state is closest to energy to our resonance stabilized carbocation, right? So if I can stabilize that intermediate, what happens to the energy in my transition state? Does it go up or down? If I stabilize it, it goes down, and so the rate goes faster. That's right. If I have something, however, that destabilizes that, so I've got a carbocation, and now I'm withdrawing electrons from that, that's going to clearly destabilize the system, right? If I take a carbocation and I try to remove electrons from that, that can't be good, right? That's going to increase the energy of activation, and so that reaction will go slow. Again, it all has to do with transition state theory, okay? The Hammond postulate. Okay. So, let's suppose we start with a substituted benzene. And according to this, you just have some group on there, which is A. The first thing that you have to do is look at what kind of substituent you have for A. Is it an electron donating group? Is it an electron withdrawing group? Then you can determine whether it's going to be ortho, para, meta. Okay? So for example, if we start off with toluene, and we put the electrophile in the ortho position, that's stabilized because why? Why is it okay for the new substituent to go on carbon number 2? When we draw the resonance structures, what do we see? What do we notice that's stabilizing about that? It's in the red box, or the brownish box, whatever that is. I have a tertiary resonance stabilized carbocation. If the electrophile was to attack at the meta position, what can I never get when I look at those resonance structures from that? I can never get the tertiary carbocation, right? That explains why the alkyl group is an ortho-para director, because if I look at the para position, the electrophile gets attacked at the para position, I can also draw a fairly stable carbocation, right? And that's why we see what we see. It's all about that carbocation stability. That's the take-home message of this slide. Okay? We'll skip that one in the interest of time. Now, if you look at nitro, which is a strong electron withdrawing group, it's a strong deactivator, right? You can clearly see why the ortho attack is not preferred. Because if the electrophile goes at the ortho position, you get a carbocation which can be resonance delocalized to where we have two positive charges next to one another. Is that a good thing or a bad thing? It's very bad. That's why the nitrobenzene doesn't direct ortho very much. However, if we look at the meta attack, what do we see? I can never get that carbocation resonance delocalized next to that other cation, right? So that is more stable or less stable than the other two? It's more stable. It's more stable. Yeah, but it doesn't matter that it's tertiary in this case because you're putting two positive charges next to one another. That's a bad thing to do, right? Now, some groups are so activating that it's very hard to control the reaction. So if Sarah came into the lab with aniline and she wanted to brominate aniline and just put on one bromine, it would be very difficult for her to do. Because the aromatic ring is so activated, it will continue to react. Okay? It's a very strong activating group. And notice what she gets out of the reaction. Those three bromines are on those specific positions, and only those specific positions. There's none of them that are meta to the nitrogen. Okay? They're all either ortho or para. The phenol is the same way. If you take phenol and you add bromine and iron tribromide, you're going to get tribromophenol. And the phenol is so activating that you really don't even need iron tribromide. If you just want to put one bromine on, you just take phenol and add molecular bromine, and it will do the chemistry of electrophilic aromatic substitution. And you can stop it by only putting on the one group. Okay? So we will finish this up on Wednesday. Now, Wednesday, we're going to finish up a few things. We will have an inverted lecture, so watch the pincast. Come prepared for that inverted lecture. I'm going to hand back your exams. The score, listen, the score that you have on here does not include the 4-point offset. So when you see that score, add your 4 points to it.